Hello. In the short video, or not so short video, I'll be talking about igneous rocks a little bit more, and specifically talking about volcano types and the hazards associated with different types of volcanoes. There are four broad categories of types of volcanoes. There are cinder cones, shield volcanoes, composite volcanoes, and dome complexes. And I'll be walking through each of these in the next few slides. Here are images from our textbook of dome complexes. This is Chaos Crags in Northern California, which formed as a result of dacite eruptions about 1100 years ago. Dome complexes are typically relatively small in size. They have very steep walls to the different features, and that's because they contain mostly of felsic magma, which is very thick and viscous, and therefore it doesn't spread out that much. The next type of volcano are the composite volcanoes, and these are your typical reversed ice cream cone volcanoes that have moderately steep slopes, a crater at the top, and are fairly large in size. This is Mount Fuji in Japan. These volcanoes consist of a variety of rock types, all the way from basalt to rhyolite. They also consist of layers, interlayers of lava flows, lava rubble, and pyroclastic flows. And the buildup of these layers is what gives the relatively steep flanks of these volcanoes. These take a while to form, several 100,000 years to form, and are quite spectacular. The next type of volcano type is the shield volcano. Shield volcanoes are composed mostly of basalt, which is a very fluid, high temperature magma, which flows easily away from the crater and forms these nice layers. Therefore, a characteristic of shield volcanoes are very shallow slopes. They can be quite high in elevation, like Mauna Loa here is 10,000 feet above sea level, but they have very, very gentle slopes, indicating formation from liquid basaltic lava, very liquid. The final type are cinder cones. Okay, these are smaller volcanoes that consist mostly of scoria from basalt, andesite, and composition. This is Sunset Crater in Flagstaff, Arizona. They have a prominent crater at the top, relatively steep sides, but very small. And these form by single eruptions that can last from 1 to 20 years in length. So those are the four main types. The fifth one is related to a process. Okay, and fifth type are calderas, like Crater Lake. Crater Lake is a caldera. Now, calderas form as a result of massive explosive eruptions of composite volcanoes as shown in this model here. And let's just walk through those steps. So here we have a nice composite volcano with relatively moderately gently dipping, that was confusing, steeply dipping sides and a magma chamber. Okay, so upon eruption of this magma chamber during a large eruptive episode, the magma chamber is somewhat evacuated. So you're losing all this mass down here, but you still have lots of material up here. So there's an opening and lots of weight overlying it, lots of mass. So you get big pyroclastic debris, and then the interior of the volcano collapses into the magma chamber, forcing out eruptions along these radial fractures. Okay, and this forms the caldera, which is a large, relatively round crater that is flanked by these pyroclastic flows. And then the magma chamber starts to build up, and you have a thing called the resurgent dome, which is what Wizard Island is. So here is the caldera boundary of Crater Lake. And it's a result of a massive volcanic eruption about 7,000 years ago of a mountain called Mount Mazama, which spread ash for hundreds of kilometers. So that's a caldera eruption, and the landform is called a caldera.
Our next topic is volcanic hazards, and before we get into specific hazards, I'd like to review in some detail this diagram from your book. I would spend some time looking at this diagram as it is a good summary of a lot of different information. So let's walk through this a little bit. On the top, we have composition of lava, okay, or magma, from basaltic or mafic up through intermediate and into felsic, the rhyolitic. Associated with this compositional spectrum, the silica content increases from 50% up to 70% in the more felsic. Now, also associated with this spectrum is a change in temperature. Rhyolitic lavas tend to be lower temperature, basaltic tend to be higher temperatures, and then the intermediate are in between. Also, these two features, the silica content and the temperature, are associated with an increase in viscosity. So this is a very low viscosity. It flows easily. It's kind of like the maple syrup of melted rocks. Whereas the rhyolitic has a very high viscosity, okay, and this is kind of like the toothpaste of lava or magma. Okay, so increased silica content, increased temperature that direction, increase in viscosity. Also, another feature of this spectrum is an increase in gas content. Rhyolitic tends to have more gas content, basaltic has less. And these factors all add up to the fact that basaltic or volcanoes that emit basaltic lava are less explosive, whereas ones that are rhyolitic are more explosive. So these can have explosiveness locally, like fountaining of lava, but they're not very big regional or global events. These types of volcanoes, the eruptions, can be very significant regional and even global events. Now, associated with all of this is the type of deposits. Basaltic, you tend to have more lava flows. You can get out of the way of those. The more felsic we have lava domes and pyroclastic deposits. Okay, so these are the different types. Now we can connect all of these to the types of volcanoes. Shield volcanoes, like on Hawaii, do have cinder cones. They're associated with basaltic lava. And then as we move into more felsic material, we get composite volcanoes, and then finally dome complexes, which form from the real thick rhyolitic lava. So spend some time looking at this diagram, and you might even think about adding rock types up here, and that would be a good summary of volcanic products and explosiveness, etc. This slide shows a model for why volcanoes that have a high gas content, which are generally higher in silica, are explosive. So here's the model. It's a champagne bottle, and here is the model of a volcano. So during periods of non-eruptive periods, the vent to the crater is plugged. Okay, so during that time, gas trapped in the magma is under pressure. Okay, and so therefore there's a buildup of energy within the magma chamber. That is akin to having a champagne bottle with a cork in it, and the gas is trapped in the liquid because it's under pressure. So if the conduit is taken out or freed, if that plug is removed through an earthquake or just buildup of pressure and fracture of the rock, the gas is released from the liquid, and when that happens, it produces a explosive volcanic event. Just like when you release the cork, you get a fusion of bubbly out of the champagne bottle. So these two models help to explain why these eruptions are so explosive. This slide shows a comparison of the size of different volcanic eruptions. So let's take a look at this. This is going to put some things in perspective in terms of our experiences with different volcanic events. So this shows how much magma erupts. It's the numbers here are in dense rock equivalents. So the greater the number, the more rock that has been emitted from the volcanic eruption. And the different colors show the volume of material erupted. So 1 cubic kilometer equals 0.24 cubic miles. So the orange colors are huge, the blue colors are small. That's basically what we need to know. So let's look at some things down here in the lower end. So we have Lassen Peak, which is one of the volcanoes that people researched. And here we have Mount St. Helens, okay, of eruption in 1980 and Pinatubo in 1991. So these are pretty small events when you look at other historic or more ancient eruptions. So Yellowstone had 3 major eruptions in the last 1.5 million years or so. Here's Mesa Falls, here's Lava Creek, and here's Huckleberry Ridge. And these are big, huge regional events. Long Valley Caldera is also a eruptive event that occurred out of California. And then, of course, there are some really huge ones, Toba, which is about 74,000 years ago. Okay, so ones that we've experienced, these two here in our lifetime, or at least in my lifetime, are relatively small. And of particular concern or interest to us are the Yellowstone ones, because this occurs in North America, and an eruption of the Yellowstone caldera, which is not imminent or anything, could be a major deal.
So let's take a little more of a look at Yellowstone. So here's the Pacific Northwest and out into the Rockies here. Here are the Columbia River basalts, which actually make it all the way to the coast. Okay, these are big regional-sized lava flows, basaltic lava flows, plateau basalts. And then here we have a series of, and then we have our Cascade volcanoes, some of which are dormant: Baker, Rainier, Helens, Hood, Crater Lake, and Mount Shasta, and Sisters is right here as well. Okay, so that's kind of setting the stage. Now Yellowstone, the active area is over here, and there's a chain of volcanoes that extends away, with the oldest one here at 16 million years. So this is like Hawaii. This is a hot spot underneath the continent. This rock here formed over that hot spot 16 million years ago. And we have a progression of ages as we get closer. So Yellowstone's located right here, currently the hot spot, and it's fueling a lot of volcanic activity in the way of hot water, hydrothermal activity. Here is a shot looking to the north in this direction. There's the border between Idaho and Wyoming and the Snake River Plain. This is one of the old calderas, the Tetons, a beautiful mountain range. And the caldera boundary is shown here in the red. So this is the boundary of the old volcano and the source of a lot of the current activity. If we look at a cross section, this is a model for what it looks like under the Earth's crust for the Yellowstone caldera. Here is the mantle, rising basaltic magma. Okay, it starts melting the surrounding crustal material and producing a granitic magma. This place is being stretched out, and we're getting a lot of flow of water, hot water, up through to the surface, producing the geysers. So notice the geysers for scale. And we have a variety of earthquakes. Okay, so this is a big deal, and the reason why it's
This map here shows the United States and the extent of ash that has occurred as a result of different volcanic events. So in the 1980 eruption of Mount St. Helens produced a relatively small ash cloud which extended to the northeast and covered parts of Washington and northern Idaho. Now when we look at some other events, the Long Valley caldera and the Yellowstone caldera, we can see just how small this is compared to other major historic or ancient events. The Long Valley caldera had an ash distribution shown by this dotted line, and the three eruptive features in the last 2.5 million years or so of Yellowstone had a much bigger regional extent, as shown here in the Lava Creek ash bed. And these are arrived at just by looking at deposits within the sedimentary record, and they can find ash beds that are correlated with the Yellowstone area. So as you can see, if an eruption of this size occurred now, the ash would extend across most of the U.S. And of greatest concern is that this is obviously a location of a lot of agriculture, and so that would have a big impact on food production within the United States.
Okay, so let's now talk about some volcanic hazards, specific volcanic hazards. So here's a model from the USGS, United States Geologic Survey, of a volcano with the magma source down here, and this lists all the different hazards. Okay, so we have the eruption cloud, which can produce noxious gases and acid rain. We have lava flows, which go away from the crater. We have the pyroclastic flows, which are clouds of hot ash and gases. We have Lahars, which are where snow melts and produces a muddy slur that goes down through river valleys. And we can also get landslides that form as a result of, or even starting the volcanic activity.
Let's take a look at some of the hazards associated with volcanoes. So this photo on the left shows an example of a lava fountain and then a lava flow which emanates from that fountaining event. This is from Hawaii. This is certainly a hazard in terms of buildings and vegetation and so forth, but most people can get out of the way, and there's probably not a lot of casualties as a result of lava flows. On the other hand, pyroclastic flows, which are shown here, are very hazardous. They're fast moving, I believe up to a couple hundred kilometers per hour. They fill river valleys as they flow down the flanks of mountains, and they can inundate villages and towns and destroy buildings and cause a lot of casualties. As you can see, these people are hustling away. So these are major events which are a big hazard to people and property. Now, it is one of these pyroclastic events that result in the casualties at Pompeii back in 79 AD. Here's an artist's rendition of the eruptive event. Lots of clouds, a very eruptive process. Here is a map that shows the smoke plume as recorded by ash beds that came from Vesuvius. Here's a location map in Italy, and notice that 3 towns were destroyed as a result of this volcanic event. And perhaps you know this story, but below the city of Pompeii, the present city, they found, they excavated ash layers and found these casts of people that had been inundated by the pyroclastic flow. And you can see this guy is just starting to get out of bed. So this is a pretty spectacular and somewhat gruesome reminder of what pyroclastic flows can do. Another spectacular example of the impact or the hazards associated with a pyroclastic flow is from the eruption of Mount Pelee in 1902. Mount Pelee is located right here on the Isle of Martinique in the West Indies. Here is a subduction boundary where the Atlantic plate dips below the Caribbean plate. Here's Puerto Rico and Venezuela in South America. And in 1902, Mount Pelee, which is shown in the background here, erupted in a massive explosive event, sending a pyroclastic flow down through the Isle of Martinique and inundating the city with this pyroclastic flow and killing over 20,000 people. In fact, only 2 people survived from this event. One person who was a prisoner locked in a cell, and another, I'm not sure how they survived. I guess they were just lucky. So obviously pyroclastic flows can be a devastating, or have a devastating impact. Another volcanic hazard are lahars, okay, and this is an example from a volcanic eruption of the mountain Nevada del Ruiz. Here is a location map. In Colombia, there's a chain of volcanoes where plates of the Pacific Ocean dip below in a subduction zone above the South American continent. And Nevada del Ruiz is located right here. In 1985, there was a major eruption which melted the glacier on top of the mountain and sent a mud flow down all these river valleys. The area that was hit the most was Armarillo here, where the mud flow spread out into the plain. And here is an example. I think over 25,000 people died as a result of this. All of this gray material is part of the lahar, this mud mixture that forms as a result of the melting of the glacier on the top of the mountain and all the volcanic material. It inundated this town and resulted in massive casualties. Another volcanic hazard are the gases associated with eruptive events. And an example from Lake Nyos in Cameroon. Here's Cameroon at the bend of the west coast of Africa. Lake Cameroon, or Lake Nyos, is a volcanic lake, a crater lake, which is located on the flanks of this active volcano. Now, this event wasn't related to a volcanic event eruption, so to speak, but the gas that had settled into this lake was trapped was due to volcanic activity. So this is a story. So below the surface of this lake in the sediment, carbon dioxide was accumulating in the sedimentary layers, and then there was a landslide into the lake which disrupted those layers and produced a CO2 cloud that came out of the lake. Now, CO2 is a little more dense than air, so it settled into the valleys. It resulted in 1,700 casualties and 3,500 livestock deaths, as shown here, because people were asphyxiated. Now, since then, they've put in pipes into the sedimentary layers to try to slowly vent the CO2 so this wouldn't happen again. But another danger in this lake is dammed by volcanic deposits. It's an area of active earthquakes, and if an earthquake event happened here, it may breach or may cause the lake to breach the dam and release the CO2, which would then travel down the valley where there are other settlements. So, volcanoes. There are obviously benefits to volcanoes. They provide geothermal energy. They provide the rich volcanic soils, which are used to grow a lot of food, especially in the Southeast Pacific. And they provide recreation, beautiful landscapes to visit. As we discussed, there are a lot of hazards associated with them, which can result in lots of casualties. And obviously there's a lot of beauty associated with them as well. Now, there are pretty good ways to predict the eruption of volcanoes. So the number of casualties usually in current volcanic events is relatively low compared to in the past, because things like earthquakes and change in surface elevation and changes in the gases emitted from volcanoes can be used to predict these. But when they do erupt, some of the outcomes, like these large clouds, which can also affect climate. There's been times or volcanic events like Pinatubo and Tambora and Krakatoa where there's actually been changes in temperature over a number of years because of the volcanic event and the resulting ash that's put into the atmosphere. So volcanoes, dangerous but beautiful.